Hello, welcome once again, and in this video we are going to discuss how to draw Newman projections. Now, this requires that you have a good 3D visualization. So to help us understand the drawing, I'm not just going to use the bond line structure, but I'm going to include the wedges and dashed lines. Now, when we use a wedge, so let us include the hydrogen so we can be able to see them clearly. When we use a wedge, it's going to imply that the bond is projecting out of the screen. So it's coming towards you. When we use a dashed line, it's going to imply that the bond is projecting into the screen, away from you. And then in carbon number 3, we can do the same. Once we have those hydrogens being visualized properly, then now we can draw the Newman projection. In the Newman projection, by focusing on the indicated position, we can identify which atom is on the front and which one is at the back. So carbon number 2 is on the front. So the front one we use a dot. And then the one at the back we use a circle. And then we need to indicate the position of the substituents. So by looking at carbon number 2, the hydrogen that has a wedged bond is going to be on your right. The one with the dashed line is going to be on your left. And then the CH3 is on the plane, that is carbon number 1. Let us go to the one at the back. So the one at the back, the hydrogen shown using a wedge, using that wedged bond, means that it is going to be on our right over here. And the other one is going to be on the left over here. And the one on the plane, that is the carbon number 4. Once we draw it this way, we can do rotations. We can do rotations around carbon 2, 3 single bond. So that bond there, we can rotate it. We can rotate so that we use carbon, that single bond, to generate different conformations. One of the conformations we could do is we can rotate it like that around 120 degrees, and we will end up with a structure that will look like this. Now remember, the front one remains exactly the way it was. We are rotating the one at the back. The positions for the ones at the back are going to move. So if we rotate it 120 degrees, we are going to have the CH3 being here, and then the other hydrogen is going to be here, and the other one is going to be over here. This kind of interaction, where the bulky groups are close to each other, we call it gauge interaction. So this kind of conformation is also called gauge conformation. In the first one, we have the bulky groups being anti. One is at the top, the other one is at the bottom. And that is at the top and back. Then the one on carbon number 2 is at the front, and at the bottom. So we call that anti-conformation, or we can call them staggered. Okay. Another conformation that we could generate is where the CH3s, the bulky groups, are eclipsed. In other words, they are aligned together. So we could have the front exactly the way it was at the beginning. Then we rotate the carbon 2,3 single bond, and we end up with a CH3 aligned there, then the other hydrogen, and then the other hydrogen. So when they are aligned with each other, we call this an eclipsed conformation. This conformation is of very high energy due to the steric interference, the steric effect. So compounds would not want to have this kind of conformation. Instead, they will interconvert to acquire the most stable. So this is the lowest in energy. So let's call this lowest in energy. So they will interconvert to exist in the lowest energy format. Gauge conformation is, again, not very stable. So like I said, these conformations are interconverting. So the molecule keeps finding a conformation that it is comfortable with. You can use a molecular model to generate other conformations, but these three are important, and I would want you to be able to recognize them and even to be able to draw them. Thank you for watching. Have a good one.